Okay then, so this is the last of the instrumental techniques that you're going to need to know about for the exam. This is probably the one that's going to challenge you the most as well. This is NMR spectroscopy, which stands for nuclear magnetic resonance. It's the principle of the MRI machine, which I'll mention a bit briefly later. But we have to understand how this technique works and how we use it to analyze compounds. So let's kick off. Okay, firstly then, let's see how the thing works. Okay, now then, you have been made aware for some time that electrons possess a property called spin. This is not to be taken too literally. It's an angular momentum, a quantum mechanical term. However, if you want to think of it as like a little spinning top, then that's fine. It's just not like that in reality. Okay, now then, as well as the electrons, the protons and neutrons also have a property called spin. And like the electrons, they have two possibilities, either a spin up or a spin down. And as you will see in the box on the left, it says, if you have a proton and a neutron together, then basically one will spin up, the other one will spin down, and they pair up, just like electrons do when they're in the same orbital. Okay, now then, we're looking at some possibilities for this technique. You will notice that there are 3 in the table that have an overall spin and 2 that don't. The ones that have an overall spin have an odd number of nucleons. That's total number of protons and neutrons. So in other words, an odd mass number. Now, if it has an even mass number, effectively the spins pair up. That causes them to cancel. And if they cancel, there will be no overall spin for that nucleus. If they don't cancel, as for example in the case of hydrogen 1 here, the proton, carbon 13 and phosphorus 31, these basically will have spinning nuclei. Now, just like any charged particle, when it spins, it generates a magnetic field. So they behave like little magnets, basically. Okay, now then, under normal situations, under normal circumstances, these magnets will basically point in random directions because there's nothing, they're not feeling any field. So effectively, they don't have any particular direction. They're all pointing in different directions. But if you put them into a magnetic field, then there's basically 2 things that can happen. They can either align with the field or they can align against it. And pretty obviously, they will align with the field if they can. Now, in this next slide, you will notice that they've shown both possibilities. Those that line with the field and those that line against. The ones that line against are effectively higher energy than those that line with. It's that energy difference that we make use of in NMR spectroscopy. So, on this next slide now, we're going to put them into a magnetic field. And of course, they will all line up with the field because they are going to be in a lower energy configuration. But if we could give those a bit of energy, then they could possibly line up against the field. A bit like atomic emission spectroscopy. If you give the electron energy, it can move from a lower level in its ground state to a higher level and become excited. And that effectively is the same kind of thing happening here. So if we now give energy, so you will see an electromagnetic wave has just come in. That particular nucleus that you just saw has aligned against the field. It's now in an excited state, but it won't stay there. It'll flip back down, and when it does so, it will re-emit that energy as a burst of energy, as it relaxes back to its low energy configuration. Now, it's that burst of energy that we measure in NMR. Why is it called NMR? Well, nuclear pretty obviously involves the nucleus. M, magnetic, pretty obviously they have magnetic fields. But what about the R, the resonance? Well, all we did just then was see that particular nucleus flipping once against the magnetic field and then relaxing back to its low energy state. However, if we keep pulsing waves, electromagnetic waves into this sample, then we're going to keep on causing that nucleus to align against the field. It's going to flip against the field, it'll flip back. It'll then flip against the field and flip back. And as long as we keep pulsing in those electromagnetic waves, this will keep happening. And that lining up, lining against, lining up, lining against, of course, is what we call resonance. Okay, so we now understand the principles of nuclear magnetic resonance. How are we going to use this to analyze compounds? Okay, let's have a look at the next slide. Now then, in a molecule, the different nuclei will have different bonds and atoms around them. We say they're in a different chemical environment. Now, those bonds and atoms around them can affect the magnetic field strength that's needed to cause the nucleus to flip. If you like, it's probably best if you think of it in terms of the electrons in those bonds and atoms that surround the nucleus. Those electrons are, like the nucleus, they're spinning charged particles. They will generate a magnetic field. It just so happens that the magnetic field the electrons generate is in opposition to the magnetic field which is applied. So effectively, they shield the nucleus from the external magnetic field. If we can measure the strength of the magnetic field that needs to be applied to a particular nucleus in a molecule, then effectively we can get information about the environment of that particular nucleus. The ones we're going to look at in this unit are carbon-13 and hydrogen-1. They obviously will have spinning nuclei because they have odd mass numbers. In the two examples shown, you will notice that on the left side we have the molecule. Do we recognize it? Do we remember this from term 3? It's 3 carbons, it'll be prop. It's got a carbon double bond oxygen on the middle carbon, and therefore it is a it's a ketone, and this is propanone. Now, you will notice that the red carbon is in a different environment to the green carbons. They are in the same environment. So you will see 2 signals for this particular molecule, one for the green, one for the red. The green signal will be twice the strength of the red because there's twice as many carbons. Get the idea? On the right-hand side, we're going to be looking at the hydrogens. So we're going to look at both of these types of spectroscopy. The carbon-13 is the one we're going to do first in this video, and then we'll do the hydrogen one in a second video because it's a bit more complex. Anyway, on the right-hand side molecule, which of course is, okay, so hopefully you just said ethanol, you'll notice there are 3 different environments for the hydrogens. The left-hand hydrogens are all identically placed, so they will obviously have 1 signal. The 2 blue hydrogens are in a different environment. They will produce a 2nd signal. And the green hydrogen is yet in a 3rd environment. You will see in this case a ratio of peaks. There'll be 3 to 2 to 1. And hopefully that should make sense. Now then, it's a bit of an unusual looking spectrum. It's not like your normal graphs, if you like. The mass spectrum, the infrared one, reasonably easy to understand. This one is a bit different. We are going to measure something called chemical shift. Now, chemical shift is the difference between the external magnetic field and the magnetic field felt by the nucleus in question, which of course will have electrons around it, shielding it from the external field. Now, we don't measure this in absolute units, we measure it compared to a standard. And the standard is a reference chemical called TMS. TMS stands for tetra methylsilane. Okay, now why do we choose this particular molecule? Well, if we are using it, firstly, you will see that there are 4 carbons in an identical environment. So they're going to produce a pretty easy to recognize signal. It has 12 hydrogens. Let me just check that. 3, 6, 9, 12. Yeah, that's right. 12 hydrogens in exactly the same environment. And they will produce a very, very obvious signal. But it's a bit more than that. Take, for example, the carbons. Now, carbon is more electronegative than hydrogen. It's also more electronegative than silicon. So that means the carbons in that molecule are pretty well shielded by electrons from the external magnetic field. So they will pretty much have a very strong magnetic field needed in order to bring them into resonance. Carbons in other molecules will not be as well protected by their electrons. They therefore will require a lower magnetic field. And we measure the difference in the magnetic field in parts per million because it really is very, very small. Okay, so in the spectrum we're going to see in a moment, we are going to assign a chemical shift value of 0 to the standard TMS, and then all others will be measured relative to that. It's a bit like electrode potentials, which you may or may not recall from last year. We had a standard, which was 0, and we measured all the others relative to that. Okay, let's have a look at the propanone molecule again, and then in a moment we'll see its spectrum. Now then, again, we have 2 different chemical environments. The red carbon is in a different environment to the green carbons. It's just reminding us that we can't use the carbon-12 isotope or the carbon-14. It has to be carbon-13. It only makes up 1% of natural carbon, but when you're measuring in parts per million, it doesn't take a great deal in order for that to be significant. Okay, so we know already that the electron density around the carbon nuclei is protecting them from the external magnetic field. Now then, which carbon or carbons will be better protected? The carbon bonded to the double bond oxygen or the carbons bonded to the hydrogens? Well, oxygen, of course, is a very electronegative element. Therefore, it draws electrons away from the carbon in the middle. So this carbon here is not going to be as well protected, as well shielded as these carbons by the electrons from the external magnetic field. Moving on. Okay, so the next slide is going to show us the spectrum. We are going to see the spectrum actually goes kind of backwards. TMS is given a value of 0, but that 0 doesn't start where you'd think it starts. It starts at the high right-hand side of the spectrum. And then we measure the difference between that magnetic field and the ones that these nuclei are experiencing. And they chemically shift downfield, so they will move to the left of that. Okay, so there you can see the 0, which obviously is the peak due to TMS. If you were actually showing that peak, it would be twice the height of that one because it's got 4 carbons. However, you will notice that this peak is only shifted by a very small amount, whereas this peak is shifted by a much greater amount. If you think about it, hopefully it should be starting to make sense. This peak is due to these carbons here. These are much better protected by their electrons than that carbon there. So they are going to be closer to the very well protected carbons in TMS. This carbon, on the other hand, is 200 or so parts per million different to the magnetic field required for TMS. What that means is it's much easier to bring this carbon into resonance because effectively it is much poorer protected from the external magnetic field. So this 200 is the difference between the magnetic field required to bring this carbon into resonance and the magnetic field required to bring the carbons in TMS into resonance. Does that make sense? Okay, let's move on. Okay, and of course you will see that the green peak is twice the height of the red peak because there's twice as many carbons. It should be worth mentioning here that don't think just measuring this height and that height is going to give you the 2-to-1 ratio. It's actually the area under the peak. So in other words, look at this bit as well, right down the bottom. Because if this bit here is wider, then this green peak will not be as high. Okay, now we're going to see another spectrum. Ethylamine or ethanamine is a molecule that you met in the organic unit we did last term. There will be 2 peaks. Let's see the structure and the spectrum of ethylamine. Okay, now we can see there are 2 carbons. Therefore, there are 2 peaks. They should be in an exact 1-to-1 ratio. Now, you'll notice this peak is slightly higher than that one, but this area is bigger than that one. So it's the area under the peak that gives you the percentage of the carbon in the molecule. Now then, the carbon here is bonded to a nitrogen. The carbon there is not. So bearing in mind nitrogen is a very electronegative element, that means these electrons are going to be pulled away from that carbon towards the nitrogen, and therefore which peak is going to correspond to this carbon here. Okay, well, like in the last molecule, this one will be less well protected, therefore will shift further downfield, and as we will see, the red peak, the red carbon, if you like, the red circled carbon, is less well protected from the external magnetic field and therefore requires a bigger difference in magnetic fields compared to the standard TMS. Crystal clear, I'm sure. Okay, so let's have a quick look to see if we can work out some of these. There's your first question. Now then, which compound of these 3 would produce this particular carbon-13 NMR spectrum? Now there are 2 peaks, meaning there are 2 different carbon environments. So hopefully you will see that this one, the carbons are identical. This one, the carbons are identical, and it has to be then ethanol. Okay, if you are actually saying which carbon was which, the one further downfield, the one that's less well protected, would be the carbon attached to the oxygen. Okay, this one has 3 different peaks. So, which of these 3 is it going to correspond to? And maybe pausing the video is easier than me just doing a pause. Okay, now you have here nitrogen is attached to this. So this is an asymmetrical molecule. Each of these 3 carbons is different. So this is a possibility. This one is perfectly symmetrical. All 3 of those are identical. Therefore, there'd be just the 1 peak. In this one, that carbon is attached to the nitrogen, but these are clearly the same. So this one would produce 2 peaks, and therefore it has to be the first one. A single peak, meaning the carbons will be identical. Pause the video if you need to, and then we will see this has to be our answer. 2 to go. 5 different peaks. 5 different peaks. Wow, let's have a look at this one. Okay, so this one here would have a peak for that one, a peak for those, and a peak for the outside ones. That would give you 3 peaks. This one, this is a tricky one. We haven't done the benzene ring yet. However, there would be a peak for this carbon attached to the chlorine. You could argue that those 2 are identical, given a second peak. Those two are identical, giving a third, and that would give you a fourth peak. So it can't be that one. However, what you will find is when we look at benzene compounds, these peaks here, that one, and that one, are so similar that they pretty much form a single peak. So in other words, you'll have one peak for that carbon and one peak for those 5 in your usual spectrum. This one, on the other hand, is an unsymmetrical molecule. These carbons and those carbons are all in different environments, and this is your answer. And finally, we have 4 peaks. Okay, let's check. This molecule here would have 1, 2, 3, 4 different environments. So this is looking like a strong candidate. This one here has one environment and a second environment. This one here has the same, one environment, a second environment. And there's our answer. Okay, now we're going to look at chemical shifts. We've already been talking about this. All right, here now is a little kind of summary. If you have the carbon directly attached to a very electronegative atom, it's going to be further downfield. If it's attached to a carbon, which is attached to an electronegative atom, that's still going to shift it downfield, but not as much. And then clearly, if there's no electronegative atoms, it's not going to be shifted much at all. You can see that peak is very close to the zero. Okay, I'm not saying any more. I think we already understand this. Looking at faces in the room as I'm saying it, and I'm looking at some blank ones. Okay, so let's see if we can get these sorted out. So which peak, A or B, corresponds to the red carbon here? We don't need data, we can do this without. It's attached to an oxygen, therefore it will be shifted further downfield and it will be peak A. This carbon here, wow, that's attached to 2 oxygens. There's nothing going to be anywhere near as close to that. This is peak A as well. This molecule here, now then, the carbon is attached to an oxygen. Let's have a look at this carbon. That's attached to a carbon. So this one is clearly going to be not as far downfield as that one, but it will be the next one. That'll be peak B. Okay. This carbon here attached to the nitrogen, peak A. That carbon there, this carbon is attached to the chlorine, that will be peak A, this will be peak B. Okay guys, too easy. Let's stop that there because this is going to be a separate video.